CR network, transient circuit. Two transient circuits that you encounter in your program of physics. One is the CR transient circuit and the other is LR transient circuit. The LR transient circuit normally we do in the chapter of electromagnetic induction. Here I am taking on a typical problem on a transient CR circuit. I'll introduce the power of Thevenin Theorem to drive my point, how you can work out any problem on the CR network. Here we are. This is a circuit. It has a capacitor of capacitance 2 microfarad, while there is a resistance R1 3 ohm in series with that. While the circuit goes, there is an EMF, voltage of EMF. There is a battery of EMF, 10 volts, internal resistance 1 ohm. While there is a switch, and of course, if you look at the left loop, then you have a resistor R3 that is 2 ohm and a resistor R2 that is 6 ohm. I can frame a lot of questions on this circuit. Well, the most important question is, what is the charge on the capacitor 20 microseconds after the switch is closed? The moment switch is closed, well, the things will start happening. And I've asked you to find the charge on the positive plate of the capacitor, because the capacitor will have two plates. The upper plate is going to be positive because that's connected to the positive of the cell. Well, how much is going to be the charge on that plate 20 microseconds after the switch is closed? The other questions I will see after we have discussed this question. Now, to work out this problem, of course, we need to know the time constant, because there is going to be an exponential charging. There will be an exponential equation. And we got to know the time constant, which I am denoting by lambda. Now, we all know lambda is C into R, but what R to take? In a simple circuit that you normally do at the school level, at the boards level and so on, well, there is a capacitor and a resistor in series. So it's so simple. But here it is not so. There are other resistors as well. There are loops. It's not a single loop. But why don't we convert this into a single loop? And that is where I am going to use the power of Thevenin Theorem. Thevenin Theorem tells us that if we have a combination of EMFs and resistances between 2 points in a network, then between those 2 points, all the EMFs can be replaced by a single EMF, that is V0, and having resistance capital R0 in series with it. I choose these 2 points AB. I choose those 2 points to be AB. So what I do now, I remove the branch R1 and C. So this branch is removed. Remove it. Then between these 2 points, you find the voltage, and that will be V0. Call it EMF or voltage. Okay. How? Very simple. So if this is removed, R1 and C is removed, that's a technique I'm telling you. So between AB, the voltage is across R2. So V upon small r plus R3 plus R2, the current multiplied by R2. So V0 will be V R2 upon small r plus R2 plus R3. I put the values are given to you. Small r is 1 ohm, R2 is 6 ohm and R3 is 2 ohm. I put down that. So 3 plus 2, 5 plus 1, 6. 6 plus 2, 8 and 1, 9. So V into R2, 10 into 6 upon 9, well, that's 20 by 3 volts. So I've got the value of V0. So V0 is, well, 20 by 3 volts. Now to get R0. R0 is in series with V0. I'm reducing this to a single loop. Now, how R naught is found? Replace, short all EMFs and only retain their internal resistances and find the resistance between AB. So here you are. If you short the cell, well, this becomes 0 here. So you have 1 ohm and 2, 3 ohm parallel to 6 ohm. 3 and 6 in parallel. 3 into 6 upon 3 plus 6, that gives you 2 ohm. 2 ohm. So RO comes out to be 3 ohm parallel to 6 ohm. Well, that is 2 ohm. Well, now the circuit reduces to the Thevenin equivalent. So the Thevenin equivalent of this particular circuit is V naught 20 by 3 volts, R naught 2 ohm, and then of course I have the R1 and C which I had removed in order to get V naught and R naught. I place it here. So here you are, 2 microfarad, 3 ohm. So what will be the time constant? Now this is single loop circuit. The time constant will be C into total R, that is R naught plus R1. So here lambda, the time constant, is C into R1 plus RO. C is 2 microfarad times R1 plus RO. RO is 2 and R1 is 3, that makes 5. So this gives me 10 microseconds. So the time constant is 10 microseconds. We have been asked to find the charge on the positive plate of the capacitor after 20 microseconds. After 20 microseconds. Well, I'm using, of course, the exponential charging equation. Q is equal to Q naught into 1 minus e to the power minus t by lambda. So this is the exponential charging equation. The graph is an exponential rising curve. I put on the figures. Now what will be Q naught in the single loop Thevenin equivalent? C into V naught. Okay, C I know, V naught we have found, lambda we know. I just put the figures. So 2 into 10 to the power minus 6 into 20 by 3 into 1 minus e to the power minus 20 upon 10, 20 microseconds upon 10 microseconds, that gives me 2. So e to the power minus 2. E is the natural log base, value 2.718. Well, okay, I just solved that. So this is 10 by 3 into 10 to the power minus 6, e square minus 1 upon e square. I just square this e, put down the value, and I get the answer 2.9 microcoulomb. That's the answer to the charge on the positive plate of the capacitor after 20 microseconds once the switch is closed. I give you another question about the maximum rate of energy dissipation in the circuit. Very easy now. So what is the maximum rate of energy dissipation? Of course, it will be I square multiplied by R, and we know that the moment we close the switch, the current in the circuit is maximum. The current in the circuit is maximum. Let me call it as I max. And how much and at t equal to 0, the capacitor behaves like zero resistance. It's a very good conductor. Remember the property of the capacitor in the discussion of the charging and discharging, that when the capacitor is fully charged at the steady state, it has infinite resistance. But at the initial state, the capacitor acts like a zero resistor, pure conductor. So there you are. So what will be the I max? That is at the instant t equal to 0, the moment switch is closed. So V naught upon RO plus R1. Easy. I get the value. So V naught 10 upon 2 plus 3. 2 plus 3. That gives me 2 ampere. 2 ampere. And then what is the maximum energy rate? What's the maximum power dissipated in the circuit? That is at the instant t equal to 0. Okay. 2 square multiplied by 5. That is the P max. And I get the answer 20 watts. I hope you have enjoyed this and learned this beautiful.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.